There you go. So sometimes you end up with what's called a perfect square, and I will explain that to you. That a perfect square is a special situation that can arise that can allow you to avoid the quadratic and then save you a heck of a lot of work. So let's look at this reaction here. We got a synthesis reaction, N2 plus O2 goes to 2NO, and it's got an equilibrium constant of 0.1. I want to know what are the equilibrium concentrations of all species when 0.2 molar N2 is allowed to react with 0.2 molar O2, and there's no initial NO. If something is not mentioned, you assume there is none of it. So this is great news because there is no initial concentration of NO. Then we know the reaction has to shift right to reach equilibrium, which is going to make this problem much easier. We do not need to solve for a reaction quotient. Okay, you only need to solve for a reaction quotient compared to the equilibrium constant when you have an initial concentration of everything. We do not have any products, so the reaction has to go to the product side. We don't need to do that. So here's what I want from you guys. While I'm writing this on the board, I want a mass action expression. We'll always start by doing that. So give me the mass action expression. See if you can't make an ice table, and then let's kind of stop there and compare and catch up. So mass action expression, see if you can't make me an ice table with this stuff. Worst thing you do is get it wrong and have to fix it. Not a problem, though. All right. So first things first, how do we do with the mass action expression? That's going to be NO squared divided by N2 times O2. Okay. Next, we got to make an ice table. Everything that's in your mass action expression gets a row in the ice table. So all three things are in my mass action expression. So my ice table is going to have 3 rows. We're going to have a row for the N2 concentrations, a row for the O2 concentrations, and a row for the NO concentrations. Now, the initial column should be the easiest column to fill in. The initial column, okay, is asking for the initial concentrations. The initial concentration of N2 is 0.200, and the initial concentration of O2 is 0.200, and there was no initial NO. So check that. How's your ice table looking? How's that looking? Okay. Next, the change column. Okay. The reaction has got to go right to reach equilibrium. What does that mean? That means the N2 is going to go down. It means the O2 is going to go down. And it means the NO is going to go up by 2x. Why a 2? Because it's got a coefficient of 2. So it's going to go up by 2x. Check your change column. Next, we're going to combine the I and C column here. Okay, so this at equilibrium will be the initial 0.200 plus or minus what the change is. That's a minus x. This at equilibrium will be the same, 0.200 minus x. And this will be 0 plus 2x. That's just going to be 2x. So mass action expression, determine what direction it's going to go, make an ice table. Now it's time to plug these values into the mass action expression and try to solve for x. And I've got great news for you. So let's plug it in. Don't try to do any algebra, though. So Kc, that's 0.10, equals the quantity 2x squared, okay, divided by the N2, which is 0.200 minus x, times 0.200 minus x. Now, at this point, you may be saying, okay, well, that's going to be 4x squared, and this is going to be, I need to FOIL, right? Typically, yes, but we could take a shortcut. Okay, in the last problem, we actually rewrote the one thing to be two, functions, okay, separate like this. But what I actually want to do is I want to combine these. 0.200 minus x times 0.200 minus x. That's really 0.200 minus x squared. And now what I have is what's called a perfect square. Folks, if your numerator and denominator are both squared, it's a perfect squared, and we can take perfect square, and we can take an amazing shortcut, eliminating a quadratic and just getting us back to algebra 1. here's the amazing shortcut. If my numerator and denominator are both squared, I could take the square root of both sides and get rid of the square. So 0.1, so the square root of 0.1 is 0.316. Now you drop the squared, so that's 2x over 0.200 minus x. And you're still going to have to do algebra, and you're still going to have to solve for x, but at least we don't have a polynomial, right? This is just good old-fashioned algebra 1. So I want you to try to solve for x now. Multiply both sides by 0.200 minus x. Combine like terms. See if you can't solve for x. And if you feel confident in your x value, see if you can't give me the equilibrium values then. I'll go over in a minute. Probably 2 sig figs. We'll go with 0.027. So I got 0.027 for my x value. 0.0273, whatever, it doesn't matter. Okay, so now that we have x, we can plug that in and get the equilibrium values. So 0.20 minus 0.0273, this is going to be 0.173. That'll also be 0.173. And then 2 times 0.027, that's going to be 0.054, folks. So now you can always, and it's always a good idea, check your work. So if we plug these values into the mass action expression, we solve for the equilibrium constant, we should get 0.1. So let's do that. So here we go. Kc equals, that's going to be 0.054 squared over 0.173 times 0.173, or 0.173 squared. And we got 0.097, close enough to 0.1 because of rounding, but 0.097, that's 0.1. So there we go. We did it. This checked out. Check. That one is way easier. Go back and look at the math we did before that break, right? The math we did on that full-on quadratic one, right? It takes way, I had to erase, right? This, at least I had enough room on one board to fit the whole problem, right? So, you know, look out for perfect squares. Not always going to get a perfect square, okay? But when you do, oh my goodness, right? It's a great, great, great feeling when you get a perfect square.